Good morning, everybody. Today is Monday, August 26th, and we are in class number 2 of ES 1060, Engineering Computing. And today, here at 9 o'clock, we'll meet face-to-face in this classroom, and then this afternoon, we'll meet over just right across the hall to the north in SM 137 for lab time. So all of the things that we talk about, you can work on in lab, and I'll be there to assist you or to help you get started in any way, or to answer any questions that you might have. All right, so having said that, let's take a look at our Moodle page before we get started on a little bit of content today, and we'll talk about where we are. So as far as our Moodle page, like I said last time, and it says on the syllabus, everything that we do in this class is going to be on the Moodle page. So my favorite thing is when everybody's in the classroom with me, but if you're not here, just make sure that you take care of the stuff on the Moodle page, and we'll move forward from there. So on the schedule, oh, somebody just walked in. Hello, William, how are you doing today? One of your other classmates. So anyway, on the schedule, which is posted here, you'll see that today on Monday, both for the lecture and the lab, that we're meeting F2F, which is just face-to-face. But on Wednesday, we'll be meeting asynchronously, meaning that there will not be a time at 9 o'clock when you show up. There'll be recorded material, and you'll work ahead on your own to have some stuff due on Friday. Okay, so I'll try to keep this up to date. Next Monday is Labor Day, so the next day that we'll be back in class together face-to-face will be on Wednesday, September 4th. All right, so if we come down here, you'll see that the work is broken down into weeks. The introductory stuff, which some of it will be due on Friday of this week, is an introduction. I'd actually like that by today, but just to introduce yourself to the class, and then read your classmates' stuff so that they can know a little bit about you. And then I'll put up an introduction myself as well, but it's much less interesting than you guys. So I've been here a long time. That's kind of my story. But anyway, so that, if you'll take care of this little introduction, and then by the end of today, after we have lab together, I want you to know how you're going to access Excel and how you're going to access MATLAB. Those are the two main programming tools that we're going to use in here. And there are just some variables about how you will be accessing them. And so when I ask you how will you access it, this is not a blue sky question. This is like, I've gotten on the system, this is what my computer will do, and this is what I'm going to do for this time forward. All right, so our time together right now is we're going to get started talking about temperature conversion scales, and I will discuss this today, but it's also on a link here if you want to go over it again. And then there's a homework problem set, as you can see, this PDF file, which you'll work on after we talk about the meaning of this. And then we'll talk about MATLAB onboarding, which is basically what we're going to do today in lab. And then your homework for the MATLAB onboarding is to complete the first 5 sections. And your homework for the temperature conversions will be to do work on the green paper and submit it through this link. So Dominic, basically, anytime that you see this little icon on our Moodle page, that means there's something that you have to do and turn into me by a certain date. So there's the deal. All right, so tell me, at this point, does anybody have any questions? Or Oz, as the senior statesman of this class, do you have anything I should add about the way I like to have homework done?
No, I think you got it pretty well said.
All right, very good. All right. So what we're going to do in this class, like I said, we're going to use 2 tools. One is called MATLAB, which is a programming environment that is sort of stereotypically loved by engineers across the world. And it stands for, MATLAB means Matrix Laboratory. And the reason, there we go. The reason that it's called MATLAB or matrix laboratories because it assumes every number that you enter into it is a matrix or an array. So basically, if you enter a single number, it says, oh, that's a matrix or an array that has a dimension of 1 by 1. So it's the easiest thing when we start working with arrays of numbers, like multiplying, like doing systems of equations. It's perfectly suited for sort of the computational needs of engineers, but it does lots of other things as well. So it's a very sophisticated programming environment. The other program that we're going to be using is Excel, and you've probably encountered Excel before, but Excel is a spreadsheet plus a built-in programming environment called Visual Basic for applications. And my colleague, Tim Glatzer, who some of you may have met, said this the absolute best. He said, Excel is not the best tool for anything, but it's the second best tool for everything. And so we teach it rigorously here because, first of all, University of Wyoming teaches it to engineers, which is important because many of you go to University of Wyoming. I'd say about 50% of my engineering students go to UW after they're done here, maybe 60, depends on the year. Economically, it's like so affordable for Wyoming residents. So back in the day, I had a lot of other transfer institutions, but right now it's about 50%. But so learning Excel is important for your future at UW or other schools. It's also important for your future of engineers. The reason that we teach it, even though it's only the second best tool for every single thing, is almost every computer in the world has it. And regardless of where you go to work, they're probably going to have Excel. So being able to put Excel through its paces is a really important thing. And if you've used it to like add up columns of numbers or fill in dates, I think you'll be pleasantly surprised with all the functionality that Excel has later on. But for the meantime, we work with these two things as computing tools. So the important difference between computer scientists and engineers is engineers use things as tools. We don't really use something because it's the most elegant or the coolest language on the planet. We use it because it's functional and because we want to solve certain kinds of problems in the real world. So Oz, for example, is going to be a civil engineer. And Dominic is interested in energy engineering, especially petroleum engineering and carbon capture. So there's a lot of different types of problems. For example, if you are staking out the center line of a highway, like if you ever drive between here and Ralston, you'll notice that the road, which tends kind of southwest, makes a couple of curves as it goes into the town of Ralston. And these are by no means to scale or accurate, but this all involves the work of an engineer making these curves so that nobody crashes into the side, so that the water drains off properly, so that it's wide enough, so that there's a lot of safety features built in, and so it will last. And it turns out that going into Ralston, and Oz, you can check on this, you can verify or disprove what I'm going to tell you right now. They are portions of 3 Euler spirals, which are mathematical functions that allow you to spin in and spin out of a curve in a certain way that feels like it has integrity and is safe for you to take in both directions. So sometimes if you ever get on a ramp, if you're driving and you feel a curve in the highway and you just think there's something wrong with this, the something wrong with it is probably mathematical, and it's probably something that wasn't planned for correctly, or they planned for something that overrode another consideration. But there's some areas like that, like if you're driving in the southern part of the state, if you're going into, you're coming out of the town of not Rock Springs, but Rock River, which is north of Laramie, and you come up on the highway, there's a place where you cannot see the highway, the curve, the elevation of the highway is so exaggerated that there's a time when you can't see where you're going. That's a bad thing. Sometimes you can't avoid it, but it's a bad thing. Another thing is sometimes if you see a highway where there's water pooled on it, it means that the curve of the highway, the super elevation, is not correct, because water always does one thing. Who wants to know? Who can tell me what water does? Yes.
installation.
That's exactly right. Water always runs downhill unless you pump it. That is exactly correct. And if you have a highway situation, you do not want to pump it. You want it to run off naturally. So that's a big part of the design. Anyway, so we use these computing, these programming environments and spreadsheet environment as computing tools. And as engineers, we always want to solve problems in the real world. So in other words, I heard, let me put this down. It's real world. And we use some different tools for this. I heard a former astronaut, a woman named Judith Resnick, say this, and I thought this was just so beautiful, but she had started her career, her academic career as a mathematician, and she switched to electrical engineering because she said, at some point, I just wanted the math to mean something. And I think that's the sentiment that all engineers can bear out. So if it doesn't mean something, at some point, I just want to go have a sandwich. You know, it's not that interesting. I want to be able to build something. I want to be able to do something. I want to project that. I want it to mean something. And that's what math does for us. So if you do enough math and you subject yourself to working with mathematicians long enough and you validate the fact that math can do this for you, math is our greatest tool, and things like this can help us so that we don't have to do day after day of repetitive calculations or guesswork. So we can do better design if we have better tools to do the math. All right, so what are we going to talk about today? We are going to talk about temperature scales. Now, the first thing I want you to know, and this will come in handy for you in your entire career, is that temperature is not the same thing as heat. These are two different things. Temperature is temperature is a potential. It's something that moves something. Heat is energy. So they don't have the same units. They don't measure the same way. They don't mean the same thing. Now, this is another problem that we encounter as engineers, is that in everyday life, people use things the same way. They say, it's really hot outside. There's a lot of heat. Well, there is a lot of heat, but there's a lot of heat because the temperature is high. And that means that things, and you also know, like if you're in your house at night, if it's been hot all day, if it cools down nicely at night and you open up your windows, a lot of heat will flow out of your house and your house will cool down. Just like me, I don't have air conditioning. I have, my husband and my father-in-law are both engineers, as is one of my sons. So you can tell what the conversations at our dinner table are like. But basically, my husband and my father-in-law designed a big part of our house, and they built it with double walls, with the wall joists that do not touch each other and insulations threaded in between them. So the house is very well insulated. For that reason, my air conditioning unit has never been hooked up. It's sitting out in my shop because we've never needed it. So these are just some other things. This is like the water on the highway, right? I could pump it, I could plug in an air conditioner, but why bother if everything works? But temperature is not heat. Heat is energy, and temperature is a potential. Okay, so that means that temperature in general is measured in degrees, whereas energy is measured in units of energy, which is a force acting through a distance. So force acting through a distance is how I'll write it for now. Now, to further complicate this, we're gonna focus our temperature discussion. We're gonna focus our discussion on temperature. We'll save heat for later. I mean, don't worry, when you get into thermodynamics, we'll talk about heat endlessly and you will love it if you're like me. It's very exciting, but for today, let's just talk about temperature. All right, so what about this degrees? All right, when in your experience, what degrees do we measure temperature in? And there's several choices. Can anyone give me a type of a degree?
Fahrenheit, Kelvin,
Fahrenheit. Kelvin.
calculus, not calculus, Celsius.
Celsius, I like that though, calculus, that's very, very good. All right, and there's another one that's commonly used in science, which you've probably not heard, which is called Rankine. Okay, well, we'll talk about all four of these. Why are there so many temperature scales? Why? Okay, well, the first reason is because Everyone in the world except for 3 countries uses something called the International System of Units, or the metric system. And metric is all based on powers of 10. When the world was going to this system of units back in the 1970s, I looked this up because I thought it was so interesting, but a lot of countries had slogans to encourage their population to use metric rather than whatever they used in general. And the United States slogan was Think Metric, which I thought was interesting, not really catchy, but the one I loved the most was from Jamaica, which was 10 times better. I just loved that because it was so indicative, because everything in the metric system is based on powers of 10. So you have a bunch of base units, and then you have a bunch of prefixes that tell you if it's 10 times that much, or 100 times that much, or 10th that much, or 100 times 100th of that much. All right. 3 countries in the world did not decide to go with the metric system. And one of them is Myanmar, which is the country formerly known as Burma in Southeast Asia. The other one is Liberia in Western Africa. And the third one is, who can tell me? The United States of America. That is correct. I love living in the United States. I'm so happy I'm a US citizen. But wow, somebody said, we're America. We're not going to do that. We like what we have, which is not even really a system. I refer to it as the US customary system because it's all come up by custom. In other words, somebody did something, everyone started doing that, and then we've done it forever and we're never going to stop. So now Myanmar has 2 main exports, one of which is illegal that I won't mention in this class, the other which is legal, which is teak wood. So their main dealings with the rest of the world, legal dealings with the rest of the world, is selling what we would call kind of like a board foot of teak wood. But there's a bonus for bigger teak trees because you can build bigger things out of them. So they use the system. Their main units have to do with measuring the volume and the length and width, and ultimately the volume of teak wood trees. Okay. Liberia actually uses the metric system. They just didn't want to ever sign a document, and they may have signed it by now, but they've been using it for years, but they didn't sign on at least until 5 years ago. I'll have to check on that to see if they have. Us, we just want to keep using what we use. All right. So what that amounts to then when we start talking about temperature is the United States started talking about Fahrenheit. And this was actually developed by a guy whose last name was Fahrenheit. So that's why we call it degrees F. So degrees Fahrenheit works like this. I'm going to get a new piece of paper here. On the Fahrenheit scale, this fellow was using water and water mixed with salt to look at physical properties of water. So on Fahrenheit scale, at 32 degrees Fahrenheit, water freezes at atmospheric pressure. At 212 degrees Fahrenheit, water boils at atmospheric pressure. When I say atmospheric pressure, what I mean is 1 atmospheric pressure. Here in Powell, Wyoming, we're at a high elevation, which means if you think about the Earth, I'm going to draw another picture down here. Here we go. The Earth is curved like this. But if you're at Santa Monica, California, you have this humongous column of air above you, and it weighs on you because everything's directed toward the center of the Earth. Here in Powell, Wyoming, we're in the Bighorn Basin, and we're about 4,000 feet higher than Santa Monica, California. And so that means that there is 4,000 feet less of a column of air above us. So that means that the atmospheric pressure here is quite a bit lower. Now, people live at quite high elevations, and a lot of people, historically, people have always lived at sea level near the sea. So the fact that the three of us in this classroom, and William, you're up by a beautiful lake, which is fantastic. But most people historically have lived at a waterfront because water provides a lot of stuff for us. The fact that we live in the desert is really a testament to modern life and engineering, because we couldn't really live here without irrigation. I mean, we could, a few of us could, but we would not be able to build a city without having water. Anyway, and living this high in elevation is not unique in human civilization, but it's an interesting, we live in an anomaly, is what I'm telling you. We are living in a specialized kind of a way that has not been available to most people throughout the course of history. But we have less atmosphere above us. So that means that atmospheric pressure here is just lower than it is elsewhere. That also means that, like, there's less oxygen. There's the same concentration of there's the same percentage of oxygen in the air as there is at sea level, but the air is more dense. And so there's more oxygen as you breathe in a volume of air, assuming that your lungs are the same size as a person at sea level will get more oxygen per breath than people up here. So there's a lot of things, but our atmospheric pressure is lower. So whenever you especially talk about boiling, freezing, there's a little effect. Boiling substances depends really highly on the pressure. So that's why we have to say at 1 atmosphere of pressure, okay? So after Fahrenheit did his work, and this is great because then you can measure things. The thing about temperature is if you have energy at a high temperature and you have a low temperature reservoir, it'll act just like a voltage difference. You know, electricity flows from high voltage to low voltage, depending on, unless you're in the Navy, then it flows the other, they have different way of dealing with it, but it's still the same idea. Water flows from a high elevation to a low elevation. Heat flows from a high temperature to a low temperature, unless you pump it. So that's what air conditioners actually do. They don't make the air cool, they bail out the heat. So it's a little different. And you'll learn about that in thermo, and it's really fun. But today, just suffice to say, if you have a heating device like a furnace, you actually create heat by burning some substance and heating an environment. But air conditioning is not really the reverse of that. Air conditioning is removing heat based on a thermostat setting, and then pumping heat out and pumping something cool in, but it's not the same at all. So when people say that, like, a heat pump run backward is an air conditioner, I beg to differ. But anyway, that's just me. All right, so here we go. So 212 degrees Fahrenheit, water boils. 32 degrees Fahrenheit, water freezes. Well, another guy comes along, and his name is Celsius, which we have now renamed centigrade, because centi means hundredth, and grade just refers to gradation or measurement. So he said 212 is a stupid number for water to boil at. I think it should be 100. So he took the exact same work that this guy did, and he said, I'm going to make this 100. So what do you think he made water freeze at? 0 degrees centigrade. So that means that 0 degrees centigrade is exactly the same temperature as 32 degrees Fahrenheit. 100 degrees centigrade is exactly the same temperature as 212 degrees Fahrenheit. Okay. Now, I reserve the right to tell you several lame jokes while we are together, not just in this class, but for our time together. So congratulations to all of you. First one's coming up right now. Turns out when we work the temperature scales, and this is all mathematical, negative 40 degrees Fahrenheit is exactly the same temperature as negative 40 degrees centigrade. And my joke for that is I was raised in Butte, Montana, where it routinely got to negative 40 degrees. It's just cold. It does not matter how you measure it. It's just really, really cold. It's kind of awful. You freeze to death in that kind of weather. Anyway, but here are the two scales these are referred to as ordinal scales. Ordinal just means the 0 doesn't really have a fixed or a totally benchmarked clear, fixed meaning. Okay, now you might argue with that, and you might say, well, centigrade does because, or Celsius does, because 0 is where water freezes. But there's actually a better 0 for temperatures, which is called absolute 0. And absolute 0, if you call 0 absolute 0, and I'll talk about what that means in a minute, 0 degrees Kelvin, also 0 degrees Rankine, which we've talked about. Absolute 0, there's almost some mystery that surrounds it, but basically absolute 0 is a couple of different things. It appears, for very much, when I say appears, I don't mean like it's my opinion. I mean, for very good practical and physical and theoretical reasons, it appears that that's as low of a temperature as could ever be attained. It is the temperature at which, you don't have to write this down, the entropy of a perfect crystalline form of a substance is a minimum. Okay, so what that basically, some people will say absolute 0 is where all molecular activity stops. Not really stops, but is as low as it can possibly be for different reasons. Okay, so what somebody else came up with was, and now we're working in science, so we're talking about the Celsius or centigrade scale. Perhaps we need a scale where 0 is absolute 0 instead of where water freezes at atmospheric pressure, at 1 atmospheric pressure. So we come down here and we make the Kelvin scale. And the Kelvin scale drops way far down. But basically, absolute 0 is way down here. Can you see that? There we go. And that is absolute 0 is 0 degrees Kelvin. The other thing I want to point out is that if you use Celsius or Fahrenheit, you need to use the degree symbol. If you use Kelvin, there is no degree symbol. It's just 0K, means 0 degrees Kelvin. All right, so it turns out that.
Negative 273.
Sorry?
I said negative 273.
Oh, so very good. Negative 273 degrees Celsius is the same as 0 degrees Kelvin. And this one I'm a little shakier on, but I believe it's negative 400. It's either negative 459 or 469 degrees Fahrenheit. So William, while I'm doing the rest of this, I'm going to let you look that up. Okay.
You got
How
it.
many? I did. Woo! First time. Excellent. All right. So negative 459 degrees Fahrenheit. Okay. So 0 degrees Kelvin. If you look at that, there's 273 degrees difference. So that means that water will freeze at 273 degrees Kelvin. And that means it will boil at 373 degrees Kelvin. All right. All right. So scientifically, we had this worked out, and this works out better in the lab. You'll also find out, so numbers have these beautiful meanings. And when you subtract them or get a delta, you can see that Celsius and Kelvin will give you the same deltas. But when you look at ratios, they're not the same. So anytime that you take one divided by another, you have to work with an absolute scale. So deltas, you can work with either scale, but ratios, you have to work with an absolute scale. So at that point, somebody else came along, and I don't think Rankine actually did this, but Rankine was a big guy in, let's put this up here. Lord Kelvin was a big guy in building engines. So I don't think he came up with the Kelvin scale, but I think he came up with a lot of the ideas that were associated with the Kelvin scale. And similarly, a guy named Rankine was a big guy in developing heat engines, actually. So he came up with a different scale that said, well, we need one that has, because Celsius and Kelvin deltas are the same size. We need something on this side where Fahrenheit and a cardinal scale, which I didn't write that word down. Cardinal just means that 0 means something. Where the cardinal scale is the same size, but we still are at absolute 0. So he, or the people involved after him, developed the Rankine scale, where 0 degrees Rankine is 0 degrees Kelvin is absolute 0. And I don't know if you use a degree symbol on Rankine or not. I can't remember right now.
It's
Um,
0 R.
0 R, or it could be 0 degrees R, not sure. We're gonna find out. But what that means is there's a difference of 459 degrees, which means not 32 degrees, but 0 degrees Fahrenheit, which doesn't really have a physical meaning, but that's the same as 459 degrees Rankine. Okay, and then we can project up here where water freezes and where water boils. I'll have to do the math on that to find out what those numbers are, because I don't remember offhand. But I'll show you how to do the math. All right. So we are at 9:30. We still have 20 minutes, so we can proceed. Before I move on to the mathy math, does anybody have any questions? All right. So let's do some engineering math. All right.
I actually have.
Yes, go ahead, Dominic.
How do you change Celsius into Kelvin? Is that
Yeah,
273?
exactly.
What's-
That's what we're gonna get to right now. So, yep, you're on. So the next question is, if these temperatures are all the same, they have commonalities, how do we change? So you are just 15 seconds ahead of me, which I always appreciate. Change, which the word for that is convert, from one temperature scale to another. All right, so the first one I'm gonna do is the more common, which is degrees centigrade to degrees Fahrenheit. And I kind of use those terms interchangeably. I should say Celsius, but Celsius and centigrade mean the same thing, but Celsius is the more accurate number. All right, so if we look at Celsius, we know that 100 degrees Celsius is exactly the same as 212 degrees Fahrenheit. And we also know that 0 degrees Celsius is exactly the same as 32 degrees Fahrenheit. So the first thing is, if we take the delta, we can see that if we go from 100 to 0, in other words, delta 100 degrees centigrade is exactly the same as 212 minus 32, or 180 degrees Fahrenheit, which means a degree Fahrenheit is smaller, has less delta than a degree centigrade, right? Okay, well, if you do the ratio, let's do it the other way. Let's say 180 divided by 100. If you reduce that fraction, you get 18 over 10, which turns into 9/5. Okay, but there's also the difference in where the 0 is. So in other words, if we started here, we say, okay, 0 degrees centigrade is the same as 32. So to go from centigrade to Fahrenheit, we must have to add 32 every single time, right? So if we start with degrees centigrade, we're going to multiply it by something and add 32. We're going to come out with degrees Fahrenheit. Well, what are we going to have to multiply it by? The answer is this number is always going to be bigger, right? So this is going to be 9/5. So there's our first formula. Now let's try it out. If we are at 0 degrees, if we put in 0 here, 0 times 9/5 is 0, plus 32 is 32, that number works. Let's check our upper point. 9/5 times degrees centigrade, 9/5 times 100 is 180. 180 plus 32 is 212, so that works, checks out at both ends of the scale. All right, now what if we go the other way? Well, instead of doing the scales, let's just solve this equation for degrees centigrade, okay? Because something a little bit different happens here. The first thing is we would subtract 32 from both sides, and we would get degrees Fahrenheit minus 32 equals 9/5 degrees centigrade. But then I need to multiply both sides of the equation by the reciprocal of 9/5, which is 5/9. And what you'll see is on the left-hand side of the equation, I have to multiply this whole parenthetical. In other words, negative 32 gets multiplied by 5/9 as well. So this is 5/9 times the quantity, degrees Fahrenheit minus 32. equals degree C. Or it's always better form to write what you're solving for on the left-hand side of the equation. And when you're programming, it's not just a good idea, it's the only way it ever works. So we just want to rewrite this equation. So it looks like this. All right, so the first part that I want you to see is that degrees Fahrenheit from centigrade or Celsius does not have parentheses. Degrees Celsius from Fahrenheit does have parentheses. And parentheses, remember the order of operations? Please excuse my dear Aunt Sally. Meaning you do parentheses first, then exponents, then multiplication and division in order from left to right, and then addition and subtraction in order from left to right. So you do what's in the parentheses first. And if you check those two numbers, let's do that. 32, if I want to go to 0, 32 degrees Fahrenheit, minus 32 is 0. 0 times 5/9 is 0, so that point checks out. Up here, 212 minus 32 is 180. 180 times 5/9 is 100, checks out. All right. You can also check this out just for fun. Still have a minute. If we want to check out, is negative 40 degrees centigrade equal to negative 40 degrees Fahrenheit? Well, the way that we can check it is just to plug in negative 40 into either of these equations. This one's easier to me. So I'm going to say, how many degrees Fahrenheit is 9/5 times negative 40 plus 32? Okay. If I do this, that's 8. 9 times 8 is 72. Negative 72 plus 32 is negative 40. So that shows you that by plugging that in, making that substitution, that negative 40 degrees Fahrenheit is negative 40 degrees centigrade. Okay. All right. So there's two of the equations that you will need. Looking back at this, the two easier ones to change from to would be Celsius to Kelvin, and then Fahrenheit to Rankine. The reason being that they have these two have the same deltas. In other words, the size of a degree Kelvin is the same as a degree Rankine. They just have a different 0. And same over here with Fahrenheit and Rankine. Right. So if we look at degrees Celsius and we look at the numbers, what we can see is that in order to get degrees Celsius, we have to take the degrees Kelvin and subtract 273. The other way, we would say degrees Celsius plus 273 is equal to degrees Kelvin. Right? All right, and then for Rankine, we kind of have the same thing where we can say degrees Fahrenheit is equal to degrees Rankine minus, and like I said, I don't know if there's one of those or not, minus 459, or degrees Fahrenheit plus 459 is equal to degrees Rankine. So there you go. Yeah. Degrees Fahrenheit is equal to degrees Rankine minus 459. And so rewriting that, just adding 459 to both sides, I get degrees Fahrenheit plus 459 equals degrees Rankine. Okay. So we have many of the equations we need. The next thing that we would have to do is to convert between kelvins to Rankine. And then if we could do that, we can convert the other scales. We might have to do it in 2 steps. We might have to combine equations, okay? But how would we do that? Well, let's take something in common. For example, here we have Fahrenheit in terms of Kelvin, and we have Fahrenheit in terms of Rankine, and we also have Celsius in terms of Kelvin. So if we do some substitutions, we can solve for degrees Rankine in terms of, say, Kelvin. All right, so let's do that. Let's start with saying, since I know that this is equal to degrees Kelvin, don't want to do it that way. I might have to rewrite that equation. but I shall if I have to. I also know, further, I know that degrees Celsius is equal to 5/9 times the quantity, degrees Fahrenheit minus 32. If I look at this, I could solve for Fahrenheit in terms of kelvins by plugging this in for Celsius up here. So I would get 5/9 times the quantity, degrees Fahrenheit minus 32, because that's a Kelvin, excuse me, a Celsius, plus 273 equals degrees Kelvin. And then if I multiply this through using order of operations, 5/9 degrees Fahrenheit minus 32 times 5/9. I should know what that is, but 9 doesn't go evenly into 32. 9 times 4 is 36. So I have to do a little old-fashioned arithmetic here. So if I take 32 and multiply it by 5, that's 160 divided by 9. Let's just leave it like that, minus 160 divided by 9. Plus 273 equals how many degrees Kelvin? So then if I combine these two numbers, 160 divided by 9, that goes in once, 970, 9 times 7 is 63, so I have a 7 left over, so it's 17.7, more or less. So if I take this number and subtract 17.7, I'm just going to call it 18 because we're in class. So that would be 565, 255 if I combine these two. So I have 5/9 degrees Fahrenheit plus 255 equals degrees K. And there's my conversion formula right there. So I can plug in any degree Fahrenheit and come out with degrees K. I could solve this for Fahrenheit and plug in K and solve for Fahrenheit instead. Okay. And then we can do the same thing. I have time. I have 8 minutes. With let me see, I should have labeled this a little bit better. This is to convert degrees Fahrenheit to Kelvin. So that means that the next thing I would like to do is to convert degrees C to Rankine. Okay, and I can kind of do the same thing because I have the Fahrenheit to Celsius conversion. And this is the other thing I wanted to tell you. This is just, I'm not naturally a person that likes to keep my papers in order. I'm pretty much better working on computers, but on things like this, you can save yourself so much time by writing out everything, at least in a fashion that's organized to you, because you don't have to go back and reinvent the wheel every single time. So that's just something that I have found. So let's start with that. Let's say degrees Fahrenheit equals 9/5 degrees C plus 32. And then we further know that Rankine to Fahrenheit has a difference of 459. So degrees Fahrenheit plus 459 is equal to degrees R. Okay, so I know that Fahrenheit looks like this. Let's solve this for degrees Fahrenheit. And I have this and I have this. And since they're both equal to degrees Fahrenheit, I can use the transitive property and set them equal to each other. And I get 9/5 degrees C plus 32 equals Rankine minus 459. And if I just bring this over by adding it to both sides, I get 9/5 degrees C plus 32 plus 459 equals degrees Rankine. And when I add these together, I get 491. So 9/5 degrees centigrade plus 451 equals degrees Rankine. There's all my conversion factors. Okay, and then once again, I can solve this, if I want to solve this for degree C, in terms of degrees R, I can do that, and so forth. All right, so at this point, do you guys have any questions? All right, so what we're gonna work on this afternoon in our lab over in SM 135 or SM 137 is we'll take a look at this homework, which is on your Moodle page. I've written out 10 problems. It says it's due Wednesday, September 6th. When you see a deadline like that, there's two things I want to alert you to. The deadlines are here for sure. They're not on, if I have something written incorrectly on a document, that just means I borrowed it from a semester in the past. The real deadlines are right here. Okay, so turns out this one is September 6th, but if this one conflicts with this one, or you see, wait, September 6th isn't Wednesday, always go with the Moodle page. This is the up-to-date information. And if you have any questions, just ask me. Anyway, so you'll submit this by Friday, September 6th. Okay, so we'll work on that a little bit in lab today. But the most important thing that I want to start working on in lab is to do the first 5 sections of MATLAB onboarding. So that means that we're going to get on the computers. We're going to find out a way to access MATLAB for you and you can get started. This isn't due until this coming Friday, but if the fates align, well, if the stars align and the fates are good to us, we will probably be able to get it done this afternoon. So that's kind of the deal. The other piece I wanted to show you was, you'll see up here, it says ES 1060 and COSI 1010. This class is just ES 1060. In the past, we have run these two classes together with some extra work. Computer Science 1010 is a 4-credit class for computer science majors, and we've given them an extra day, but we've done it at the same time. We're not doing that this year because in addition to a computer science program, we've also started a software development program, and they take Computer Science 1010, and the curriculum for that class has become different enough and theoretical enough that we can't run them together anymore. So from now on, for the foreseeable future, ES 1060 will be a standalone class. But if you ever see that, that's the origin story of that equivocation. All right, so that's it for today, you guys. Does anybody have any questions?
Yeah. Hey, Astrid. I'm
Yes, sir.
probably not going to make the lab. I have work.
Yeah,
I have work scheduled on Mondays for the foreseeable future.
yeah. Well, William,
So are Zoom meetings recorded?
yes.
Okay.
They are. This one will be recorded. In lab, if it's exciting, I'll record it. Sometimes it's just me walking around talking. I mean, like the first part of it I'll record, but you probably don't want 2.5 hours of me just like sitting at my desk, right? That's not too, I mean, I think
Right.
it's exciting, but you know, but
Yeah.
anytime that you have any problems or questions, I will record everything that has any content in it. And then the other thing is, do you see our Moodle page on your screen right now? Or no?
Yes.
Okay, so if you go to this program right here, this link calendly.com,
Yeah.
always schedule an appointment with me and we can Zoom, or if you're on campus and you want to meet face to face,
Sure.
just come by my office. But let me know so I'm sure that I'm there. How does that sound?
That sounds good.
All right, so yeah, there's 1,000 different ways that we can visit without you physically being in lab if that's not your thing. It's the most efficient way to get your work done, but it's not a requirement. So,
Sure.
all right.
Sweet.
All right then. All right, guys, I'm going to stop recording. Thank you for a good class, and I will look forward to seeing some of you this afternoon and talking with others of you as we go through this material. So have a great day.